when I was invited to talk at SGP, I was kind of thinking about what kind of problems I want to talk about. And after looking at what I had been doing and what other people had been doing, say in recent years, I chose to talk about what I would call human-centered geometry processing. And let me explain what I mean by human-centered. So if we look at geometry processing, which was, what we saw as geometry processing when SGP was just started, about 2003, and what we had been doing for many years, when we think about what I would call classical or traditional geometry processing, what we are doing in geometry processing very often is solving well-defined geometric optimization problems. So we're solving problems such as, for instance, parameterization, where we know what we want to get, and our challenge is to come up with an algorithm which will give us the result we want, whether we are looking at very old work or at things which are much more recent, or we're looking at problems such as hexahedral meshing, where we know, again, we want to take an input, and we want to split it into cuboidal elements with certain well-defined geometric properties. Or perhaps a more recent flavor, looking at fabrication problems, where we want to, let's say, take 3D objects and break them into parts which can be fabricated using different techniques. The common denominator in those problems is that we know what our goal is and we can formulate that goal in mathematical terms. However, there's lots of geometry processing problems which are kind of have an inherently different flavor. So this is one example. You have what you have here, you have a raster image and you want to vectorize it. And I'm assuming each one of you in the audience can immediately imagine in your head how the result looks like. Namely, you know what you want the result to be. However, if you start thinking about how do I formulate the goal of achieving this result in terms of a geometric problem, that's where it becomes a bit more challenging. Or another example, let's say I want to tell you, I want an algorithm which will take the functionality of one object and combine it with the style of the other. So again, I'm assuming everybody here can easily imagine how would a chair which has this style should look like. So as humans, we know what to expect. However, when we try to think about what kind of function we want to optimize, or what kind of mathematical constraints we want to impose so as to achieve this result, that's where it becomes a whole lot more fuzzy. So this is the type of problems that I think of when I talk about human-centered problems. The common denominator to those problems is, as humans, we know what we want to get. Intuitively, we can visualize the result in our head, but we don't know how to express this goal in mathematical terms. Now, what that means is that before even trying to solve the problem, we need to somehow go from the human expectations, the ones which we kind of know what we want, but we cannot necessarily quantify, and formulate those as a geometric optimization problem. Now, once we have that problem, we still obviously need to solve it, and solving it can still be pretty hard. But before we even get into the point of solving it, we need to get to the formulation. And in my talk today, I will talk about how can we approach this type of formulation. And, well, how did people do it in the past? Well, if you look at computer graphics or geometry processing, the traditional answer used to be, well, we come up with something such that the results look right to us and hopefully look right to our reviewers as well. And hey, we solve the problem. And it's not necessarily a really bad solution, because very often, what looks good to a bunch of people is probably the right thing. But as we try to make geometry processing more rigorous, we want to try and do better. We would like to quantify a little bit more accurately. How do we measure human expectation? And in my talk, I would like to look at some examples of ways to do it. How do we try and provide an optimism, and quantify human expectation using different tools, and also look at some common threads in this space. Let me start with a fairly simple problem. You have a sketch drawn by an artist here, and you have a character. And what we would like is to have an algorithm which poses the character to match the sketch. And I'm guessing this is more or less what you would have imagined as the pose conveyed by this drawing. Now, the interesting question is why? Why is this the right pose? Why, for instance, you don't think that the arms of character maybe are pointing a little bit to the front, or maybe the knee of this character is a little bit bent? There is a lot of ambiguity in this drawing if you kind of think about it. The same contours could have conveyed different poses. Yet, I'm assuming most of you had predicted this to be the result. Now, even further, if you actually look closely at this drawing, you will notice that the drawing and the proportions of the character do not exactly match. Even though the artist was asked to draw this particular character in this pose, the length of the arms, for instance, with respect to the body, is not the same. So there is a lot of ambiguity in this task. You can have different poses which could theoretically fit this drawing. Yet somehow humans choose a particular one, and we would like to have an algorithm which chooses the same one. So what goes on here? Well, this is where we need to think about viewer perception. Like, why do viewers choose a particular pose? Part of it has to do with familiarity. We are choosing a pose which is kind of not very weird, a pose which is very common. But even among the more common poses, we know that we are choosing this particular one, rather than some of the others. Why? And big part of the answer lies in Gestalt psychology research. Gestalt psychology research had investigated for many years how humans interpret 2D data, and it gives us a whole lot of hints as to choices people make and assumptions that we make when we look at 2D drawings. And those are the assumptions which probably went in your head, even though you maybe didn't think about them when you chose a particular pose. Something which is also interesting to note is whenever we talk about drawings, particularly drawings by artists who are professional, those artists are quite aware of human perception. And when they make their drawings, they make choices in the drawing such that when the viewer looks at the drawing, they will see the pose that the artist intends. So for instance, if the artist wanted to convey a pose where the knee here would have been bent, well, maybe they would have slightly rotated the view, maybe they would have exaggerated the kneecap here so as to pay attention to it, to somehow communicate to the viewer the fact that they are looking at a less simple or less straightforward pose. So I'm not going to go into the detail of this particular algorithm, but I'll just briefly talk about the cues which we speculated and employed when generating the poses from the drawings. And one very important one was this idea of fidelity or descriptiveness. And that's the idea that humans really are going to choose the most simple pose which is consistent with the drawing. Therefore, if an artist wanted to have more complexity, they would have found a way at the drawing level to communicate it. We also leverage the fact that, as we said, we're looking for simple poses, poses which are natural, not something which is very heavily contorted. And lastly, another thing that perception studies tell us is that humans prefer regular interpretation. And part of that means that, for instance, when we're looking at poses, we assume symmetry. So even though we don't see the back, leg, and arm, well, we interpret this pose as being perfectly symmetric on those limbs. So once we have those cues, once we have this collection of concepts which tell us what humans want, now we can come up with a geometric optimization problem which balances those cues. And we can solve this one in this particular case. We have used discrete graph embedding and optimization in order to solve this problem. So at the high level, I think the key take home from this example is this notion of leveraging perceptual cues. when we are trying to understand what humans want, perception literature is a very useful source. If we can find information there and we can use it, it will help us a lot in our attempts to formulate the problem. Here's another example. Here is a 3D curve network. And I'm guessing each one of you can exactly imagine in your head the surface that this network is interpolates. Namely, when you look at it, you can see every curve loop as describing a clear bounded surface patch. Now, why? Why is that the case? Here's another curve loop. It's kind of an abstract example, yet I'm assuming in your head, everybody has an opinion of what the surface bounded by this loop is. Is this what you expected? Probably not. Is this more consistent with what we want? I would think so, yes. So why? Why is this the solution that people expect? And how do we understand what the solution is? Now, because we are looking at 3D data, perception literature is somewhat less useful because a lot of the perception research is focused on 2D. However, what is very useful is to ask, okay, those are not random drawings. Those are drawings made by designers. So designers make certain choices as to which curves to use when communicate, for instance, this shape. So let's try and understand what curve designers draw. And if we look at design literature, it's going to give us the answer. Now, notice that what we are making here as an assumption is that designers use curves which are effective at communicating shape, which means that the curves they draw are consistent with the curves that humans expect. So what do designers draw? Well, if we look at design literature, it tells us that designers really focus on two types of curves. One of which is view dependent, and that's contours. So it's not helpful for the problem we are looking at. We are looking at 3D inputs. The other one, which is view independent, is what designers refer to as dominant flow lines. What is dominant flow lines? Well, once you go into design literature and try to translate from designer speak into geometry speak, a flow line is inherently a curve which is aligned with principal curvature directions in anisotropic areas and then is smoothly extended across isotropic areas. And if you kind of look at the surface you imagined here, you will see that indeed this definition is consistent with what you expect those curves to be. Now, what dominant means? Well, it means that there is nothing interesting happening in between the curves. So the area of the surface in between the curves is really defined by the curvatures along them. So those lines are sufficient to define what happens in the middle. Now notice that once we have this definition, we now can really look at the classical geometry processing problem. Because now we can think about searching for a surface whose curvature field matches the flow field implied by the input flow lines. And we can even go as far as to define these goals in terms of a classical integration problem on the surface, where we look at the difference between the flow field and the curvature field. And now we can look for a surface which minimizes this integral with respect to our initial flow lines. Now, we do have one small problem. In order to evaluate this functional, we need the fields. But you cannot define a field unless you have a surface. So how do we solve this? Well, we use an iterative approach, which is something fairly common in geometry processing. We start with some initial surface, which is not necessarily very good from our perspective, as in the curvature along it and the field induced by the flow lines are far from aligned. But now once we have the surface, we can compute the fields across it. And now we can modify or deform the surface to better align those fields. And we can then repeat the process until we obtain a result we want. Here are a couple more results. Here are a couple of two networks and the surfaces obtained from them. So I think key to this example is leveraging modeling conventions, namely looking at domain literature and trying to understand the users. trying to understand why users make certain choices. And then once you can understand that, you can quantify those choices and come up with an algorithm. Let me look at one more example, which is quite different. And that's an example of sketch consolidation. So what is sketch consolidation? Sketch consolidation, you can think of it as a mental process of taking a raw artist drawing and understanding the 2D geometry or the 2D curves which those artist strokes depict. Presumably, if I were to ask you, what does this drawing depict? This would be your answer, right? So these are the meaningful curves depicting the different parts of the shape drawn by the artist. The process from going from one to the other is often referred to as consolidation. And what this process really does, it locates groups or clusters of strokes, and that's what you are doing in your head, even though you might not think about it, but this is literally what you do. You are locating groups of strokes which jointly depict a single curve, and then you're imagining inherently the curve that those clusters or groups jointly depict. So if we want to do this task algorithmically, we really have two separate components. The first one is going from strokes to clusters. So understanding which group of strokes jointly depicts a single intended curve. And then once we have those groups, you actually go and depict or compute those curves. And today I will only focus on this part, and I will ask the same question we had asked before. What makes humans make the choices they make in the grouping so that we can now come up with an algorithm which replicates those choices? Well, here is a small example. Can you mentally imagine the clusters? Is this the clustering you created? Now, can you think why? Well, let's look at perception cues and what perception literature tells us about how humans do grouping. And for that, let's look at this example, where again, hopefully each one of you almost instantaneously here grouped the strokes into different clusters. Now let's look at the cues which you likely employed when doing it. Perception literature tells us that one of the most dominant and important cues when it comes to grouping shapes, and in this case specifically strokes, is proximity. Now, what we mean by proximity is not absolute distance, but relative proximity. And that's the idea that within every cluster, the strokes are grouped, are distanced roughly equally, while the distance between different clusters is much larger than the distance within every cluster. And the fact that the relative distance is very important, because if I look at these strokes here, which come from the head, if you notice this distance here between those two groups, which we as humans perceive as different, is actually very similar to the distance here internally inside this cluster. Yet in this case, because all the strokes have roughly the same distance, we see them as being together, while here, this distance is much bigger, the internal distances within those two smaller groups, and therefore we see them as separate. So this is what relative proximity tells us as a perceptual principle, and we can use that principle in our grouping. Another fairly basic observation would be that when we are looking to cluster strokes, we really expect strokes in the same cluster to be roughly parallel, while strokes which have a sharp angle are likely to belong to different clusters. Lastly, a third and very important criterion is we are not looking just at groups of strokes, we are looking at groups of strokes which jointly represent strokes. So groups of strokes which jointly represent curves. If I look at this group here, those strokes here are roughly parallel and they are equidistant. But kind of the width of this group is much bigger than its length, so intuitively it's not a stroke, it's not a curve, right? For something which to be a curve, we expect it to be long and narrow. So narrowness is a third cue we can employ. Once we understand the cues, we can employ them in an algorithm, and we can also think about how you, for instance, or me, or anybody observing this data had employed those cues in those three examples. And we can also formulate cluster criteria, which is essentially what we are looking for, is for distinct narrow clusters of locally parallel, roughly evenly spaced strokes. Now, once we have this criteria, we can come up with an algorithm. In our work, we suggested a coarse-to-fine approach, which looked at first average properties, so average distances, average angles, getting us coarse clusters, and then looking at local compatibility, so assessing distances internally, let's say at every individual point, pairs of points on adjacent strokes to get a fine clustering. And I'm intentionally not going into the details of the algorithms. You can read the papers if you want more details. Once we have the clusters, we can perform the fitting. So is that enough? Or did I just hide something under the rug when I was describing this algorithm? I did. Because when we think about the question of are strokes angle compatible, or are strokes proximate enough or relatively proximate enough? Is a group of strokes sufficiently narrow to be deemed as a curve versus just a different type of group? All of those require thresholding, right? We need some kind of threshold which will tell us are things sufficiently parallel. Traditionally, very often, what computer scientists do is we play around with our data until we find thresholds which seem to work on most of the data. But it would be very nice if we could come up with more valid, more principled solutions for finding thresholds. And in this work, we used two ways of finding thresholds. One was going back to perception literature. Perception literature have done a lot of studies. Many of them sometimes can help us, in fact, find answers to this type of Boolean thresholding questions. For instance, for angles, there's existing research which suggests a threshold for when people do or do not perceive things as parallel. Another alternative, which is what we used in this paper for relative proximity and narrowness, is to use particularly designed perceptual studies, where we asked, for instance, people to assess relative proximity. We showed them several strokes, and we asked them how many groups of strokes or lines they saw. We then changed the spacing between those lines and saw at which point, how far can we move things around for the answer to change in order to arrive at a value at which people go from seeing, let's say, one cluster versus two versus three. So that gives you another very important tool for trying to quantify human expectations, as in how do we come up with measurements. So trying to look at principal threshold settings. Can we use existing sources, or can we design studies which will give us our thresholds? Now let me change pace a bit and talk about very different flavor of geometric problems, and this is problems which are related to style. And style is inherently a very perceptual and a very human concept, right? It's not a geometric tool. It's not something we can easily measure, but we would like to be able to measure and manipulate it because humans do come in handy. So for this, humans are very capable of answering questions about style similarity. If I were to ask you which of the objects here, the houses, B or C, is more similar style-wise to A, I'm guessing pretty much everybody would answer that B is more similar. And so what we would like to do is, and what we wanted to do in this work was to come up with an algorithm which replicates this ability. Now notice that this is a pretty challenging problem because we would like to be able to assess style differences across objects with very different structures and functions, similar to humans. If I were to show one of you this bed and those two dressers and ask which of the two dressers is most stylistically similar, I'm guessing pretty much everybody would answer B, even though beds and dressers have very, very different topology, very different structure. So humans are very consistent in performing this type of tasks, and we would like an algorithm which can do the same. So in a way, what we can think about it as a goal is to enable relative comparison. Now, in order to do that, we suggested to come up with a pairwise style distance, which measures a distance between two objects. Now, noticeably, this is not an absolute metric. I mean, the same as for humans. I cannot really ask somebody, how similar style-wise two objects are? Give me a number between 0 and 10. Most people won't be able to do it. But if I show them 3 objects, now the comparison becomes meaningful. So the goal of this distance function is to be used for relative comparison, not for absolute evaluation. So how do we even approach this goal? How do we measure style similarity? Well, one thing we can do is to look at domain literature. So look, if you look at this example, here we have this several different types of churches. Yet presumably all of you, if asked which ones are most similar, will point to those 2 as being the most similar ones. And when we look at architecture literature or literature on furniture design, it can give us some pretty strong hints, because what it points to is the presence of recurrent, similarly shaped, salient elements as an indicator of style similarity. And in particular, if you look at the objects we have just looked at, we'll notice that indeed we have many such similar repetitive elements. Now notice that they're similar, they're not identical. So once we kind of have this observation, we can think about, let's say, the type of geometric features we may want to look at on the different objects. And we can think about how to try and leverage those to come up with a metric. So what we could think of doing is we can look at our input shapes and identify potential matching elements. And we would then like to use those elements to measure some kind of salience metric or some kind of distance metric, which will tell us how far the different objects are. Now, what we are totally missing here, of course, is the importance of the different geometric features. Like, what does it mean for 2 parts to be kind of geometrically similar? Are we looking at curvature distributions? Are we looking at Laplacian functions? Are we looking at scale? What properties are we looking at? Well, we can think of a bunch of features, but we need to somehow to weigh those features. And this is where we need human data. Luckily for us, as we said, the type of task that humans can easily do is this comparative task or comparative assessment, where people given 3 shapes can fairly consistently tell us which pair of shapes they perceive as being more similar. And what we in turn then do from an algorithmic perspective is, once we have this data, and you can collect quite a lot of it because those are easy questions to ask, and therefore it's an easy data to collect, we can then use this data in order to learn the algorithmic parameters such that the response likelihood, the known human response, is maximized. Okay, and again, I'm skipping all the details here, but the take-home message here I would like to get is this use of human data. And what we're also going to look at is here some examples of results. So what we asked people is, here is the object, here are the other 2, and then we compared our results, the one which is highlighted in green, is consistently the one which our algorithm gave, compared to the ones given by the plurality of respondents. So with both plurality of respondents and our algorithm thought that those 2 columns were more similar to one another than this one to this one. Overall, when we look at the results across multiple data sets, we have a pretty high agreement, again, with the human plurality. Notice that humans are also not universal in their opinion. There is some divergence, but there is also a strong common preference. So 85% of respondents in general agree with the plurality response, which is on par with our algorithm output. Well, at the high level, what we have leveraged in this algorithm is this idea of using domain knowledge when we have it, because domain knowledge is extremely useful, with a large-scale human preference study. And I emphasize the preference because one of the challenges when you do human studies is to ask people questions they can easily answer. Preference is an example of such a study. Let's look at a very slightly different problem in this space, and let's see what other data we can use to learn important, let's say, cues about human perception. So this is a problem you have already seen me mention earlier, and that's the one of taking the function of one object, this is the target, and combining it with the style of an exemplar. And I would venture to say that this is probably the result we would all want to get, or something very similar to it. So if we think about the problem and what are we trying to solve, we can think about it as a constrained optimization. We want an output whose style is as close to the style of the exemplar as possible, but whose functionality is equal to the target functionality. Namely, we want this output to still be a chair, which is kind of useful requirement. Now, style similarity, we have just discussed. How can we measure style similarity? And as we just mentioned, we can cast it as looking for having objects which similarly shaped elements, both volumetric and curve. However, we do need, if we only look at style, well, we can get outputs such as this one, which is not what we want, right? So somehow we need to think about how do we constrain the outputs to keep the function of our source or our target. So what we want is we want to constrain the editing operations we perform in order to generate the output to operations which are compatible, namely ones which preserve functionality. And the type of operations we look at from a technical perspective are either substitution, so taking, let's say, parts from an object and switching them with replacing parts on the target, or deformation operations, which take curves on the target and replace them with curves on the style exemplar. However, the challenge is we need to somehow learn compatibility. And this is a pretty complicated function, right? Because we don't want to really, learning function is a very complicated task. Understanding functionality is hard. So can we come up with data or source which will help us do what we want without really very heavy lifting? And the answer for us, luckily, is yes. We have online multiple sets of objects which all have literally exact same style and have exactly same style elements. But those elements are used in different places on those objects. Now, the placement of those elements on the object literally tells us what can and cannot be substituted. What operations, what edits we can do, such that the shapes retain their functionality. So for instance, we can learn from this data that if you take the legs of a bed and swap them to the legs of an armchair, those are still legs. Functionality is not affected. And so what we did in this work is we indeed used this big collection of existing data to learn our functionality or compatibility constraints, getting the results that we want. And here are a few examples. So what you have here is, this is your functionality target, and this is your style source. And kind of the key tool used in this work was leveraging of existing data with desired properties. So if the data is there, that's probably one of the easiest things to do. It's not always the case that we have it, but if we do, it's extremely useful. Now let me get to this circle example from earlier, and let's think about clip art vectorization. So the goal of three-part vectorization is you want to take drawings or raster images created by artists and convert them into vector form. Now, what kind of vector output you want? Well, you want an output which is consistent with human expectations. Here are 4 possible solutions. Which one of those would you like, or which one of those do you think is most consistent with this input? My guess is this is the one you prefer. This is indeed the one which comes out of our work, but the question here is why? Like, what goes on into this? Like, why do we as humans strongly prefer this result rather than the others? And perception literature gives us a bunch of cues which we can use. For instance, it tells us that probably humans prefer results where the outline of the vector is closer to the outline of the raster, or the outline of the vector is more simple, it consists of more straight lines, more simple curves. Perception literature also argues that humans usually prefer continuous interpretations with less corners. And lastly, it argues for preference for regularity, which is interpretations which, for instance, preserve symmetries. The question, however, is how do we combine all of those cues? Because we have several of them. And for instance, if you look at those 2 inputs, this is the one from before, this is the second one where, again, I'm pretty sure you all have an opinion about how the vector should look like. And let me give you 2 options for each. Which ones of those do you think are the right vectorizations? My guess is those are the 2 that you have picked. Now, notice, however, that if I look at the different cues, they argue for different solutions. If I wanted a solution which is more accurate, I would pick those 2, which is good for this case, but not as good for here. If we wanted a solution which is more continuous, we would want to pick this one here, but definitely not this, right? So we need to somehow have a principled way to learn the balance between those cues. So here again, we come to the fact that we need data or human input. The question is, what data is useful? For example, you can think of pairs of raster and vector images. How do we get those pairs? Well, how about vector images and their rasterizations? That's data we actually have or can easily generate. Can we use that data? Well, here is a raster image. What vector source do you think we used to rasterize to create it? This one. This is not, however, what you want the vectorization of this object to be, right? Because whatever rounded corners maybe this vector had, they are gone and forgotten by the time we rasterized it. As observers, we definitely don't expect them to show up again. So we cannot use this type of data. Inversion is not useful. What about, hey, have artists generate vectorizations? So we can take raster, have artists generate vectorizations and train from those. Problem, it takes artists forever, which means 30+ minutes to generate a single output. Unless you have very, very deep pockets, generating hundreds or thousands of such examples is just simply not going to be affordable. So we need to have some mixture. We can look at a combination of perception priors and human input. And when we think about human input, we really want to think about what kind of input we can provide such that it will give us enough accuracy and the results will be accurate, but the amount of human effort will be sustainable. Now, in the 2018 paper, we chose to go with corner annotations. Namely, our observation was that if we can detect the corners or the locations where humans expect vectorization discontinuities, then once we have those corners, we can perform the rest of the fitting without needing any extra human input. However, manual corner annotation requires quite a bit of work and quite a bit of effort. So in our most recent work, which we presented at SIGGRAPH', we took a different approach. The key observation there was that we can, in fact, take our raster and approximate it with a polygon using perceptual cues without requiring pretty much any significant amount of human input. As in, we could guide this algorithm using cues derived from very compact human studies, and then we can learn corner annotation, namely which of the corners on our polygon corresponds to an actual corner in the actual final fit versus which one should be rounded or smooth in the final fitting from human annotation. It turns out that this approach requires significantly less human input and it produces better quality. Now, there's a tiny bit here that I hadn't talked about yet, which is how do we measure better quality, right? How do we know that an algorithm which is trying to solve a human-centered problem is actually successful? Well, since your readers and your reviewers and the authors are human, well, one thing we can obviously do is just observe the results visually. So here is a raster input, here is the results of 2 earlier methods, and here is the result of our most recent method, and hopefully you would all agree that it looks better. However, this is not really sufficient. We need human validation. And yes, while authors are humans, our opinions do not really count because we have some inherent biases. So what do? Well, you want to conduct a study where you collect indeed human input and ask observers to assess the quality of your results. In this case, since we are trying to improve on previous work, the natural question to ask is which result is better, or which vectorization is better. And in this case, indeed, all participants in our study agreed to a large degree that our results are consistently better than the results of the prior methods. The key thing here is to note that you really need this perceptual validation. Your personal opinion as an author does not count. I wish it was. It would make my life as an author much easier, but it doesn't. Lastly, let me look at one more problem very quickly, which is very different from the others. So this is a problem of trying to look at data which humans create using VR interfaces. What the lady here is drawing when she is complete is this 3D collection of ribbons created using this VR interface here. Now, if we look at those type of drawings, it's kind of interesting that they all clearly communicate shape to human observers, suggesting that this can be a very interesting way of creating 3D content. And so we would like to be able to look at those ribbons that people create and create 3D reconstructions from them. Now, as geometry processing people, probably the first thing we would think about is, hey, there are piles and piles of geometry algorithms which can be used for this. Why not use one of them? For instance, how about we treat those ribbons as triangle strips? Sadly, if we do that, essentially all the methods out there break catastrophically, generating shapes with some insane genus numbers and component counts. We can also think about taking those ribbons and, approximating them using point clouds, be it sparse points along the ribbon spines or dense points on the ribbons. Sadly, yet again, this data totally kills all existing surfacing algorithms. We really tried. These are just 3 examples in the paper. I think we list like 10 methods we have tested. They all catastrophically collapse. So we are back to this problem of, hey, we have data. This data visually to us as humans looks as clearly communicating shape. So how do we use this data? Sadly, we don't have conventions that we know because this is a very new medium. Humans happen to draw this way, but there is no literature which tells them why draw this way. There's also no perceptual priors because nobody had researched perception of ribbons in 3D space up to this point. So what can we do? Well, we can look at data and identify characteristics. So what we have done is we've done an observational study asking people to draw shapes, here specific shapes or just random shapes they felt like drawing using ribbons. And something you may notice in this rendering here is there is this blue and green. What this shows is the normals to those recorded ribbons. Now, you might notice that the normals can flip quite arbitrarily. So the tangent of the ribbons, in general, the tangent surface is aligned with the surface people want. The normal can be, the orientation can be flipped. One of the reasons is because the VR interfaces use double-sided rendering. So users are just not aware of the normal that is recorded as part of the data. Now let's look at other cues we can look at on this data. Something you notice is those ribbons are pretty much lying on the surface. So really what we kind of want is we want to form our meshes by connecting vertices on the ribbon spines. The question is which vertices we want to connect. Some of those are obvious. If we have consecutive vertices along our strokes or ribbons, we want to connect them. Then, what about other criteria? How do we connect across strokes? Because if we don't, well, we won't get a surface. And yes, we want to connect points which are spatially adjacent and have compatible normals, but that's not sufficient, right? Because if we only use those cues, we're back to classical geometry, and we have seen that those methods fail. So let's look at other properties. So if we look at points on the surfaces, which kind of mentally we expect to be close to one another on the surface, we'll notice that at the level of the strokes, they commonly have similar tangent directions. And that's a fairly strong hint. And even more important one is the matches we are looking for are very often, or the adjacencies are persistent. So if I look at a pair of samples on two adjacent strokes that we expect to be connected on our surface, then we typically expect the immediately adjacent pair of samples to be similarly connected. And what this hints at is that we can cast our problem as a persistent matching, as a variant of a Markov field problem. Now, we also want outputs which are manifold, which slightly complicates our problem, slightly as in making it NP hard. However, we can, and I'm not going to discuss the details, develop a targeted efficient solution which leverages those principles I had mentioned earlier. And so this is a result on those inputs you have seen before. So this is an example where when we try to answer the question of what humans want by using observations. And contrary to all the prior settings, we kind of have to invent the wheel here because there is no prior literature. To summarize my talk, I think human-centered geometry processing is a very major component of the type of geometric operations we as researchers or practitioners want to do. And the success in this case is measured as alignment with human expectation. Therefore, the core challenge, or the first challenge we want to address, is to formulate those expectations in geometric terms. Then, once we can do that, our second challenge, which is still very hard, though I haven't talked much about it in this talk, is to solve this problem. So how do we try and get to this point of converting expectations into a geometry problem? Rule number one, I would say, don't reinvent the wheel unless you absolutely have to. Look at prior research, whether it's in human perception research or domain-specific research. Often those sources will tell you a lot of the answers to the questions you're looking for. Second is use data whenever you can, because data will give you a lot more information, specifically if you want to not just look at here as a cues, which kind of point you to the right direction, but here is how to measure those cues, how to balance them, or how to threshold them. Now, the challenge here is you want to both look at the data as in conduct observational studies and have quantitative studies which will give you actual numbers. The challenge is to collect the right data and to collect just enough data, because often collecting data is hard and time consuming. Thank you for your attention.